Hi, this video deals with the analysis of root finding methods. Let's start by discussing stopping criteria. That is, how do we decide to stop the iterative process? We'll say that a sequence xk of approximation converges to a root alpha if the limit of the sequence is alpha, or if we take alpha to the left-hand side, if the limit of the sequence of absolute errors is 0. Now, if we divide by the root alpha, we can equally say that the limit of the sequence of relative errors is 0. Okay? This is the limit for k tending to infinity. In practice, we stop the iteration and deem the approximation xk good enough if the relative error in absolute value is smaller than a prescribed tolerance. Of course, this is not a practical stopping criterion because alpha is not available. Alpha is precisely the root we are looking for. And for this reason, in practice, we approximate the relative error by replacing alpha by xk plus 1. The rationale being that, from the point of view of xk plus 1 is a better approximation that can be used to judge the quality of xk. Okay? So in practice, we use this stopping criterion based on the relative variation of the approximation. Okay? Of course, if xk tends to alpha, it is also true that the limit for k tending to infinity of f is 0. So we also use this other stopping criterion based on the value of f. Okay? It's important to use simultaneously these two relative errors, the one on x and the one on f, okay, to make sure that simultaneously x changes only by a small quantity and f is small enough, okay, to ensure convergence both for the case of flat and steep f's. Okay, let's discuss the analysis of root finding methods. Why do root finding methods converge, and why do they converge the way they do? We'll discuss two concepts, that of consistency and that of convergence. Okay? We'll be mainly focused on iterative methods that can be expressed in the following way. We start with an initial approximation to the root, and we iterate with the help of an iterative function phi that acts on xk to yield xk plus 1. Now, the properties of the scheme depend both on the iterative function phi and on the root alpha under analysis. We will illustrate this analysis by means of Newton's method. Remember this method where we go from xk to xk plus 1 by evaluating both f and f prime and xk. Okay? This method corresponds to a definition of phi of x as shown here. In other words, what we're saying is that this is simply phi of xk with this definition here. Okay. Now, consider an iterative scheme phi, like the one we just saw for Newton's method, and a root alpha. Okay. We will say that the iterative method is consistent if and only if alpha is a fixed point of the iterative function phi. Okay. The idea is the following. If we iterate xk plus 1 as phi of xk, of course, we expect this iterative method to stay still if xk equal alpha. We wouldn't want an iterative method that if alpha is known, it recommends to move away from alpha. So that is consistency. Convergence. From a practical point of view, of course, we also need the method to be convergent. That is, we need the limit for k tending to infinity of the difference between xk and alpha to be 0. Some definitions regarding order of convergence. Okay. We say that a sequence of numbers xk converges linearly, that is, with first order to alpha, if the error k plus 1 and the error k are bounded like that for a lambda that is smaller than 1. Okay. Indeed, we need a lambda smaller than 1 to ensure that the errors decrease. Whereas we say that the convergence is of order p if the error k plus 1 and the error k are bounded like this with power p here. Okay. The most usual convergence of order p is for p equal to, that is, xk plus 1 minus alpha smaller than lambda xk minus alpha to the power of 2. This 2 is what quadratic convergence means. We saw here an example for a given function f of z, and what we're seeing in these two graphs are convergence plots. So in the x-axis we have the number of iterations. In the vertical axis we have the relative error in the solution for the left plot and the relative error for f in the right plot. Okay? We have methods A, B, C corresponding to the three methods we saw in the first video on root finding. And we have, as previously discussed, these two relative stopping criteria, one based on the solution set and another based on f. Okay? These tolerances shown here correspond to this value and this value. Okay? So maybe you want to pause the video for a few seconds to think which curve is which method. Okay? And the solution we can see here. Note how this linear convergence corresponds to the bisection method, whereas both Newton's method and the secant method have a much faster convergence. Okay? So in the analysis that is following, we want to understand why. Why does Newton's method converge so rapidly? We're going to do convergence analysis. Again, it's going to be general for a general iterative method of this type. And let us assume for the moment that the derivative of the iterative function evaluated at the root alpha is different from 0. Now, let us do a first order Taylor expansion so that we can express xk plus 1 as phi of xk. Okay? This is phi of alpha, but because the scheme is consistent, phi of alpha is alpha, plus a first order term involving phi prime of alpha plus higher order terms delta k, okay? Which means that asymptotically error k plus 1 and error k are bounded by this expression where ACF is the so-called asymptotic convergence factor, which plays the role of scalar lambda in our definition of first-order convergence. This is how we conclude that if phi prime of alpha is different from 0 and smaller than 1 in absolute value, then the iterative method converges linearly. Okay? Whereas if phi prime of alpha is greater than 1 in absolute value, then we cannot ensure convergence. Consider now a more general case where phi prime, phi 2 prime, and up to derivative p minus 1 is 0 at alpha, okay? Whereas phi p derivative of alpha is different from 0. Okay? Well, in this case, we need to invoke more terms of the Taylor expansion, and we end up concluding that xk plus 1 and xk are bounded like this. In other words, we conclude that in such a scenario, the iterative method has convergence of order p. Let us see how all this applies to Newton's method. Let us show that Newton's method is consistent and convergent, and then let us discuss the order of convergence. Okay? So recall that we are talking about xk plus 1 equal phi of xk with the iterative function defined as x minus f of x over f prime of x. Let's start with consistency. Assume that alpha is a root of f, that is f of alpha equals 0. Let's check the value of phi of alpha. This is alpha minus f of alpha, f prime of alpha. So this is 0. And let us assume for the moment that f prime of alpha equals 0. Okay? So we are assuming that alpha is a simple root of f. Alpha cancels f, but not f prime. Okay? So we can clearly see that this then equals alpha, so we have concluded that Newton's method is consistent for simple roots. Now, what about convergence? So, if phi is x minus f over f prime, we need to differentiate this to obtain 1 minus, now this is f prime squared, f prime squared minus f2. Let us now evaluate phi prime in alpha. So this is 1 minus f prime of alpha squared minus f alpha f2 prime alpha over f prime of alpha squared. Okay. Now this term is 0, and we conclude that this derivative is 0. Okay. If we derivate again, we're skipping the details in this video and leaving this as homework, and evaluate the second derivative in alpha, we conclude that it's different from 0. Okay. And if we retrieve our definition of convergence of order P, we conclude that Newton's method converges quadratically for simple roots. So we have concluded that Newton's method is consistent and convergent with order P equal 2 for simple roots, and we're leaving open the question of what happens for roots of multiplicity n. Okay, that is what happens if f alpha equals f prime alpha equals f derivative m minus 1 alpha equals 0, but fm alpha is different from 0. Okay. What happens with the consistency and convergence of Newton's method in this scenario? This we're leaving as an open question. It is important to note that Newton's quadratic convergence is asymptotic. That means when we're close enough to the root. So as we can see in this plot, convergence may be relatively slow, almost linear for the first iteration, but as soon as quadratic convergence kicks in, then the increase in accuracy is very rapid. Now, homework. What happens with Whittaker's method? Whittaker's method is a simplification of Newton's method based on the following idea. Whereas Newton's method requires computing the derivative f prime of x, that's Newton's method, in Whittaker we replace f prime by a constant slope s. Of course, each iteration is cheaper, we don't need to recompute the derivative, but what happens with consistency and convergence? Okay? Now, this is left as homework. Let us finish by discussing so-called hybrid methods. Hybrid methods are based on combining two ingredients, the robustness of the bisection method in order to get closer to the root. Okay? Bisection method is slow but robust. Okay? And the rate of convergence of Newton's method or secant method or any other similar method once we are close enough to the root. Okay? For instance, we can think of a hybrid method based on combining bisection and secant. Okay? Or we can think of Brent's method, which is in fact the method coded in function f0 of MATLAB that combines the following two methods: bisection and inverse quadratic interpolation. Inverse quadratic interpolation means that for three approximations a, b, c to the root and their images fa, fb, and fc, we feed an inverse quadratic function. What do we mean by inverse? That x is a quadratic function of y, not the other way around, and take the value of y equals 0 as the next value of x. Okay? Let us finish by illustrating this idea in the following plot. So in an xy plot, we have points A, F, A, B, F, B, C, F, C. So an inverse quadratic function would like something like this. And this is our next iterate, xk plus 1. Okay.